Now next result is prove that the Kronecker delta is a mixed tensor of second rank. Solutions: delta PQ is a mixed tensor of rank 2. That is, we want to show that. Now, if it is a mixed tensor of rank 2, so this can be written as delta bar ij, which is equal to delta pq by definition, curly x bar I, curly x by p, curly xq over curly x bar j, right? Because one is contravariant and one is covariant. So this is by definitions. Now from this, curly x by q, curly x by j into delta pq. Now this q is common part, so this q is replaced by p. Then this will become curly x bar I, curly x by p, curly x p, curly x bar j. And again this product will lead to curly x bar I over curly x bar j. So it means delta bar ij, this values. So left hand side and right hand side are equal. So which is a true. So it is a true, then it means delta PQ is a mixed tensor of the second rank. Next theorem is if A bar I, which is equal to curly x bar I over curly xr, which is equal to AR, right? So this can be written in the form of A raised to power k. Now this A bar is written in the form of A. Now our purpose is to find the value of A in term of A bar. So simply we multiply this term, this term, this if we multiply this term curly x by k over curly x bar I on both sides, right? So if we want to find out the value of this term, right? Now what is this term? This is curly x bar k over curly x bar I into A bar I. Now here we know that A bar I, right? To find this product, we multiply this term on both sides to equation number 1, right? So when we multiply this term, so this will become left hand side, this values, and right hand side will become curly x k, curly x bar I, curly x bar I, curly x r into AR. So this curly x bar, they cancel to each other. Remaining is delta k to r into AR. Now r is common, so it is converted into k. So this is equal to AK. So this product is equal to AK. So simple. Our purpose is see this result and see this result and multiply this term on both sides. So we will find the value of AK. So this is first theorem. Number 2, next theorem, delta ij is invariant. So what is our claim? It's a bar and it's without bar, it should be same. Now by definition, this can be written as delta bar ij, which is equal to delta pq, curly x bar I, curly x p, and curly x q, curly x bar j. Now take this is term with this term. So this will, now again q is common. If q is common, so this term will be, this q is converted in the p. If this converted into p, so this product again this cancel to each other. We get curly x bar I, curly x bar j. So this is again, we can write it as curly x I, curly x j, right? So what is this? This is a delta ij. So this term is delta ij, right? So it means second property delta ij is invariant. Next is symmetric property remains unchanged by tensor law of transformation. So our purpose is symmetric property unchanged by tensor law of transformation. Now let APQ is symmetric, right? So by symmetric property, APQ can be written in the form of AQP. So our claim is कि A bar ij should be equal to A bar ji. Then symmetry property will be unchanged. Now by definition, A bar ij, this is in term of APQ. So this is by definition curly x bar I over curly xp, curly x bar j over curly xq into APQ. Now by symmetry property, this value is equal to AQP. So here we get these values. Now this can be rearranged in this form. So what is this? By definition, it is A bar Ji. So that is our result. On similar line, skew symmetric property remain unchanged by tensor law of transformation. Again we take APQ, which is a skew symmetric. It means APQ, which is equal to minus AQP. Our claim is A bar ij, which is equal to minus A bar ji. So it means by definition, A bar ij, which is equal to, this is a law of transformation. Now this term APQ, this can be converted into minus AQP. So this will become minus time this and AQP. So what is this? It is minus time A bar Ji. So it means again it holds the symmetric property in bar coordinates. Now from this, what we conclude? We conclude symmetric and skew symmetric properties are intrinsic property of tensor, right? So that is a proof. The proof of this result is also the same. After that, this is very important result. A symmetric tensor of second order has 1 by 2 n into n plus 1 different components in n-dimensional space V, right? Now, let Aij, we take the contravariant. So we take contravariant. We can also take the covariant. So here we, in order to prove the result, we take contravariant tensor. So we take Aij be a symmetric tensor of order 2. So by symmetry property, Aij is equal to Aji, which is equation number 1. Now I is running from 1 to n. Similarly, j is running from 1 to n. Then it means a total component are n into n, which is n square. So number of its all component are n square. Now this n square can be written in this form: a11, a12, a1n, similarly a2n, a22, a33, a3n, a2n, an1, an2, an3, an. So these are n square components, right? Now from these n square components, these diagonal entries, which are where I and j are equal, they are independent components. Why these are independent components? Because other satisfies symmetric property. A12 is equal to A21. A13 is equal to A31, right? So A14 is equal to A41. Because of symmetry property, only these diagonal components are independent. What are these components? These are n. So total component are n square, from which n component are independent. So remaining component where I and j are different, these components are n square minus n. These components are n, total component are n square, total component are n square, and independent are n. So remaining components n square minus n, right? Now, but due to symmetry property, they are in pair. A12 is equal to A21, A13 is equal to A13 is equal to A31, and so on. So they are in pair. If they are in pair, the number of distinct components can be written as 1 by 2 into n square minus n due to symmetry property. So distinct are its half. So distinct are its half, then it means the number of distinct components are 1 by 2 n square minus n. Hence total component of distinct components. So first was n, now remaining is 1 by 2 n square minus n. Then total number of distinct components, which is n plus 1 by 2 n square minus n. So this is equal to 1 by 2 n into n plus 1. So this is our result. Next result is a skew-symmetric tensor of rank 2 has 1 by 2 n into n minus 1 independent components in n-dimensional space. Now, again, we take contravariant tensor, which is a skew-symmetric. By definition of skew-symmetry, Aij, which is equal to minus Aj I. So when I and j are equal, in that case, Aii, which is equal to minus Aii, so 2Ai equal to 0. So all diagonal entries are 0. It means n entries are 0. So what we get? We get a distinct component n square minus n. So distinct components where I is not equal to j. So these components are A12, A21, A13, A3, and so on. Now these, because of skew symmetric property, this is negative to this is negative to this. If we ignore negative sign, then they are equal. If we ignore negative sign, then they are equal. They are in pair. If they are in pair, then n square minus n component appear in pairs. So total number of distinct components are its half because they appear in pairs. So 1 by 2 n square minus n. So these are the total component of distinct independent components. Now, if mixed tensor APQ, it is a mixed. P is contravariant, Q is covariant, is symmetric in one coordinate system. So in one coordinate system, it is a symmetric. Then it is not symmetric in any other coordinate system. It means the previous result is applicable only contravariant, covariant tensor, but it does not applicable to mixed tensor. Now, in order to prove this result, let this is a symmetric tensor. So we take symmetric tensor. Symmetric tensor mean APQ, which is equal to AQP, right? So this is symmetric in a coordinate system. This and x bar is another coordinate system. So this term can be written in this form. This is a law of transformations. Now interchange P and Q and I and J, right? So this is A bar QP, AGI, curly X bar Q, curly XJ, curly XI, curly X bar P, this value. Now by symmetry property, AGI can be written in the form of AIJ. Then this is same, this again same term. Now from equation number 1 and 2. So from equation number 1, this is A bar PQ. Its value is defined in equation number 1. So its value is defined in equation number 2. First term is equal, Aij equal. Second term is distinct. Third term is again distinct, different. These are different in equation number 1 and 2. Similarly, first is same. It means 1 and 2 are not equal. If not equal, then we get A bar PQ, which is not equal to A bar QP. So it means that this is not satisfied. This result is not applicable in mixed tensor. After that, very important result, show that velocity of fluid at any point is a contravariant. This is a contravariant tensor of order 1, right? So we take the position coordinate depending upon time, coordinate of point on the fluid. This is xi of t because it is a function of t, and its velocity is noted by vi. So this is a vi. Position coordinate is by xi, velocity is a vi. Now by definition of velocity, this is dxi by dt. Now coordinate of xi is transformed to new system, which is x bar I. Then v bar I, which is equal to dx bar I over dt. So this can be written as, by chain rule, curly x bar I over curly xi, curly xi or curly t, dxi over dt. So we introduce this variable. Why we introduce this variable? In order to find the value in term of vi, right? So this will become v bar I, which is equal to curly x bar I, curly xi, which is equal to vi. So clearly it is a contravariant tensor of order 1. So this is by law of transformations. Show that curly AP by curly XQ is not a tensor even though AP is a covariant tensor of order 1. We know that it is a tensor. Now it means if this is a tensor, then it is not necessary that its derivative is again a tensor. So its derivative is not a tensor. So first take, this is AP. So that is related by A bar I, which is equal to AP curly XP by curly X bar I. So this is a definition of covariant of first rank, right? Now differentiate with respect to X bar J. We differentiate this equation with respect to X bar J. Now if we differentiate with respect to X bar J, so we differentiate this with respect to X bar J. So remember, bar is differentiate with bar variable and simple is differentiate with simple variable. So bar is differentiate with bar variable. This is differentiate with simple variable. So remember this. Now differentiate with respect to x bar j. So we differentiate this term with x bar. Now this is a derivative in term of product. So first we differentiate this term. So this will become curly square x. So this term here, correct this term that is written in this. So first we take derivative of this term, which is curly square xp over curly x bar j, curly x bar I, ap as it is उतना ही सट ਇਹਦੇ ਨਾਲ ਲੱਗ ਜਾਏਗਾ. So this will become curly x bar p, curly x bar j, curly x bar I into ap, right? So here we take derivative of this term, right? Now this term is written in the same form. Now we take derivative of p, ap. Now we cannot differentiate this term with respect to bar. So we will introduce a new variable which is non-bar. It means that we will introduce q. So first we differentiate this with respect to q, and q differentiate with respect to bar j, right? So this term is same, curly x p by curly x bar. Now we want to differentiate, I repeat once again, we want to differentiate this term with xj bar, but we cannot differentiate directly with x bar j. So we introduce a simple x variable xq. So first we differentiate curly xq, then curly xq is differentiated with respect to curly x bar j, right? So we get this term. From this term we can easily analyze that this is not a tensor. Why? Because of this term. The law of transformation is in this form. So this is not tensor. It will be tensor if this term will be 0, right? So that we will discuss in the later lecture. So here we only conclude that this is not a tensor because of this term, right? So this is our result. Now these are the simple, as we learned in continuous and many other function, and now sum of two or more tensors of same rank and type is also tensor of same rank and type. Simple. Sum and difference. If we take sum, then they are of same rank and type. Same rank and type means same order. Now same in case of subtraction. Now if aijk, bijk are tensor, so it is a tensor of type 2, 1. This is 2 ij. This is 1. So 2, 1. So sum is again a tensor of type 2, 1. Contravariate variable 2, covariant 1. Similarly, in case of subtraction, contravariant variable 2, covariant 1. So it is again tensor. Now next is outer product. So simple, outer product. This is a simple product. The product of two tensor is a tensor whose rank is the sum of the ranks of the given tensors. Now for example, now if aij, it is a contravariant tensor and it is a covariant tensor. When we multiply outer product, then its rank is 2, 0. It is of order 2 and rank, type is 2, 0. It is 0, type. When we take the product, it will convert into tensor of C, ij, ij and k. So contravariant of second rank, covariant of second rank. So it is type 2, 2. So its order is 4 and its order is 2, its order is 2 and total is 4. So left hand side order is 4 and right hand side order is again 4. So this is a outer product. Very important result contraction. What is contraction of a tensor? If in a mixed tensor, this is a mixed tensor, Aij, Pqr, we put one contravariant and covariant indices equal. Now, these are contravariant indices, these are covariant indices. If we put one contravariant is equal to one covariant variable, for example, J equal to R, the resulting tensor is of rank 2 less than original tensor. So it is clear. One is subtracted from this, one is subtracted from this. So total less is 2 from the original tensor. So if J and R are equal, J and R are equal, so this tensor will become AIR PQR. So basically this R is treated as nothing. So it means AIAPQ. So its order is 3, its order is 5. So rank will be shifted from 5 to 3. And this process is called contraction. So remember, in contraction, we put one contravariant variable into a covariant variable. And the new tensor will be rank 2 less than the original tensor. So this is a contraction. Next is inner product. So outer product, we read outer product. Now inner product. So inner product basically outer product, but it is followed by contraction. If it is followed by contraction, that outer product is called inner product. So by the process of outer multiplication of two tensor followed by contraction, then this is called inner product of two tensor. Now next is quotient law. Quotient law. If a quantity x is inner multiplied by arbitrary tensor and the result is again tensor, then it implies x is a tensor. So if a quantity x, if we want to prove any quantity, is it tensor or not? If this is a quantity x and we inner multiplied by arbitrary tensor and the result will become a tensor. So this implies x is a tensor. For example, find outer product of two tensor. So this is Aijk, right? And this is BPQ, right? So its order is 3, its order is 2. 1, 2 contravariant, 1 covariant. Here 1 contravariant, 1 covariant, right? Outer product, that is simple multiplication. Aijk, BPQ, right? Now, if we take these terms in bar, so first we take A bar, Ij is related to Lm. We can choose any variable. So if I don't try to choose same as I written in this, so you can take different from IJKPQ. You can choose any variable different from IJKPQ. So here I take A bar Lm and A bar N. So this is related to this Aijk, right? Now this first take contravariant, curly x bar L, curly x bar M, right? That is related to Ij, so curly xi, curly xj. Now we take contravariant, so that is in lower part, curly x bar N, that is related to K, so that is on upper part. Similarly, B bar RS, because that is related to PQ. Now multiply. Now this you multiply. Now what you get? 1, 2, 3, 4 and 5. So what is this? It is a law of transformation. So this is C bar, LM and R, LM and R, and this is NS, N and S. This is I, J, P, K, Q, right? This relation is a law of transformation of mixed tensor and its order is 5. Why? 1, 2, 3, 4, 5. Right? Again 1, 2, 3, 1, 2, 5. 1, 2, 3, 4 and 5. So this is a outer product of this values. How we can find the inner product? So say the difference is one contravariant variable right in the form of covariant. They should be equal. Now take I is equal to Q. So I is contravariant and this is covariant. So if we take I equal to Q. So inner product, the inner product is this is first write A bar PQ, then write this IJK. Now here I is taken in the form of Q. So B bar QJK. This is equation number this. Now multiply. This is multiply, right? Multiply. Now carefully, this see that this curly x bar Q and curly x bar Q, they cancel to each other. That is in this result. Okay. So what is remaining part? Remaining part is curly x s, curly x u. What is this? This is a delta su, right? This is a delta Kronecker delta su. Clear? So this Kronecker delta is attached to one of these tensor, S and U. So we can attach it in first ARS. So when we multiply by this S and S cancel to each other, the remaining is ARU into BUVT, right? So what is this? 1, 2 and 3. So it is a mixed tensor of rank 3 because it has 3 derivatives. If it has 3 derivatives, so it is a mixed tensor of rank 3. Clear? So prove that contraction of tensor is a scalar or invariant. So do it yourself. So this is, we already discussed the definition of contraction, right? So these are very important result. So